This is my final build for the SAR ADC. Note that this SAR design was created by Mitsuru Yamada, and a link to his work is in the description of this video. Before I go into the step-by-step process, here's the output result. As you can see, when I change the analog input from 5 volts, as shown on this blue LED, where a binary 127 is shown, to 0 volts, and a binary 0 is shown. Here is Yamada's schematic, which I will be using to explain the circuit. The circuit begins at the first IC chip, 74HC273, which holds 8 D-type flip-flops. In this video, I'll be referring to this chip as IC1. The wiring configuration around this IC puts the output of one flip-flop into the data input of the succeeding. This creates what is known as a shift register. And as shown, this configuration allows for 8 bits to be stored using only one data input. All the wiring configurations are the same, except that D0 is connected to 5 volts. The next chip that is used is the 74HC74, which holds 2 D-type flip-flops per chip. Each flip-flop has its own clock, clear, reset, etc., while the 273 does not. In this video, I will refer to these flip-flops as second stage flops. The Q outputs for IC1 are connected to the clock inputs for these flip-flops. The Q output for the second stage flip-flops are then connected to an AND gate input, where the other input is the previous Q output from IC1. Each gate output is then connected to the R2R ladder, where Q0's out is the MSB and Q6's is the LSB. All configurations are the same except for the MSB, where its other input is 5 volts. At the start, all IC1 outputs will be set to 0, and all second stage outputs will be set to 1. This is because in the last step of the previous approximation, once Q7 has been shifted to high, it will flow to clear all IC1 pins and also preset all second stage flops to 1. For our demonstration, let's say our desired analog input voltage is 3.45 volts. Before the first clock cycle, Q0's AND gate will go high because one input is connected to 5 volts and the other is 1, like all other second stage Q outputs. The reason no other AND gates are high is because all Q inputs from IC1 are 0. Ultimately, this means that 2.5 volts will be the resulting ladder output. This means that the comparator output will go high because 3.45 volts is greater than 2.5. The comparator output is then connected to all second stage data inputs, which will set us up for the first clock cycle. When the first clock cycle occurs, the 5 volts from D0 shifts to Q0. This causes the second stage first flip-flop to shift out the 1 from the data line, causing 2.5 volts to essentially lock on the DAC output for the rest of the 7 clock cycles. Also, the preset 1 on the second stage second flop will AND with Q0, causing 1.25 volts to add to the initial 2.5 volts in the ladder. At the same time, Q0 flows to the D1 input of IC1, which will get ready to lock in the second MSB value for the rest of the process. And since 3.75 volts is greater than the input of 3.45, the comparator output will put a low on all data inputs. So in the second clock cycle, D1 shifts out to Q1, which shifts the 0 from the data line to the second flop output, locking in a 0 in the second MSB. At the same time, the third MSB goes high, as its preset high Q output is ANDed with Q1. Then the comparator checks if the 3.125 volts, which is the sum of 2.5 plus 0.625, is less than 3.45, which it is, so the comparator shifts out a 1 to the data line. This process repeats itself 4 more times, getting closer and closer to the desired voltage. In summary, every clock cycle does 2 things. First, it locks in the previous, more significant bit state, which could either be a 1 or a 0. And it also sets up the current, less significant bit to test if it should be high or low in the final output. During the 8th and final clock cycle, the LSB value is locked in. Then, depending on this switch state, one of 2 things happens. First, if the switch is to the right, the procedure described at the start happens, where all pins are cleared and the second stage flops are set to high. This is called continuous mode because the ADC will repeat itself as soon as the first approximation is complete. When the switch is to the left, it is controlled by a button, and when the button is pressed, it will approximate once and keep the output the same after. I wasn't able to figure out why, but for some reason 2 clicks are necessary on the button in order for it to give an accurate result.